Welcome to Calculus 3, video lecture number 4 on the cross product. So in the previous lesson, we examined the dot product in which multiplying two vectors yielded a scalar. And in this section, we're going to consider the cross product, which is also sometimes referred to as the vector product of two vectors. And this calculation allows us to multiply two vectors in such a way that the result will be a vector, okay, not a scalar quantity. Now, as a note of caution, the cross product is defined in three-dimensional vector space. So it's defined in V3, or you could apply it and use it in two-dimensional vector space with letting z equal 0, with the third component equal to 0. This is different from the dot product. Remember, the dot product worked for n-dimensional space. So here's the definition. If you have two vectors A with components A1, A2, A3, and then vector B with components B1, B2, B3, then the cross product of A and B is written as follows. So you write A, use an X to represent that you're taking the cross product, B, and the first component is A2, B3 minus A3, B2. The second component is A3B1 minus A1B3, and the last component is A1B2 minus A2B1. And you might be looking at this and think, how in the world am I ever going to memorize that? Don't worry, we're going to use matrices, in particular determinants, to help us. So the formula can be super difficult to apply. So therefore, it's common for people to use determinants just as a memory device. Taking the cross product doesn't actually involve a determinant. It's just a device that we use to help us remember the formula. So if you'll remember, when you take the determinant of a 2 by 2 matrix, so if the entries of the 2 by 2 matrix are A, B, C, D, and then remember, when you see those straight lines on your matrix, that means we're taking the determinant. When you take this determinant, you take this diagonal product here, so A times D, minus the other diagonal product, B times C. Okay, that's the rule for a 2 by 2 matrix. Now, as I mentioned just a second ago, a cross product is not technically a determinant, but the methods used to calculate determinants can be used to evaluate cross products. And we do this by setting up the following 3 by 3 determinant. So the top row, remember our unit vectors, I hat, j hat, and k hat, that's where they go. And then the two vectors whose cross product you want to take, a, b, c, so say one of the vectors is a, b, c, and the other vector is d, e, f, okay? If you're taking the cross product of those two vectors, then you stack them in rows 2 and 3 of the matrix, and then you take its determinant. And if you'll remember how to take the determinant, what you do is you take the entry. You can expand along any row or column, but in this case, we're going to expand across the top row. So we're going to take that first entry there, which is I hat. And then remember, you cross out the column and row that entry's in, and then you multiply that by the determinant of the remaining 2 by 2 matrix. Well, what would be the determinant of that matrix? It would be BF minus CE. Okay, now I'm going to move on to the next entry in the top row. And remember, the signs alternate. So now I'm going to have negative j hat. I'm working on this one right here. And then I'm going to cross out that row, cross out that column, and I multiply by the determinant of the 2 by 2 matrix that remains. So you're going to look at the matrix AC in the top row, DF in the bottom row, and that determinant would be AF minus CD. So that one's done. And then now I'm going to move to the last one, K hat. That one's positive. And then you're going to cross out that column, cross out that row, and then multiply by the determinant of the 2 by 2 matrix that's left, which is going to be AE minus BD. Okay, and then I can write this using our other notation for vectors and components. So the first component would be BF minus CE. The order of subtraction reverses on the next one because of this minus sign. So it would be CD minus AF. And then the last component would be AE minus BD. Okay? Good. So let's practice. Calculate the cross product of 2, 4, 0, and then negative 3, 1, 6. And then we're going to try the cross product and reverse the two vectors. So we're going to see if the commutative property holds. What's your guess? Stake your wages now. Okay, so I'm going to set up my 3 by 3 matrix. Top row is I hat, J hat, K hat. First, I'm going to list 2, 4, 0, because that vector came first. And then negative 3, 1, 6. Okay. And then it's totally fine if you want to skip the I hat, J hat, K hat part and just go straight to writing it in each of the components in vector form here. So you know you're going to have I hat times the determinant of what's left over here, this 2 by 2 matrix. So this is going to be 24 minus 0. Okay, now the next component, and I'll show you my little trick here. Since we know we have a minus sign, right, on this one for J hat, if you need a reminder of why, you can review your matrices, and when you're expanding a matrix, finding the minor and the cofactors. It has to do with that. Okay, since you have a minus sign and the order of subtraction is reversed, here's a trick to help make your life easier. Instead of taking this product minus this product, I do them the other way around. That way the negative's already taken care of. So I will do this product, which is going to be 0, minus this product here, which is 12. And then now I don't need to worry about adding in an extra negative. Okay, good. Now let's move on to the last one, K hat. So this is going to give us our third component. Cross out that column and row. And the determinant of the 2 by 2 matrix that's left over is going to be 2 minus negative 12. So 2 plus 12. All right. And then we're left with 24, negative 12, and 14. Okay, now let's try it in the other order. And honestly, you're going to be taking so many cross products throughout the semester. If you can skip steps and do this in your head, great. So I'll show you a cool trick that I use. I don't even write out the 3 by 3 determinant anymore. So if I'm taking the cross product of negative 3, 1, 6, I just stack them like this, negative 3, 1, 6, and then 2, 4, 0. And in my mind, I imagine that there's an I hat, a J hat, and a K hat here, okay? And then you just start taking your cross product. So the cross product of these two, in my mind, I'm imagining that I'm doing this, and then I go, okay, that's gonna be 1 times 0, so 0 minus 6 times 4, so that's negative 24. Okay, then you erase that part. Now I'm moving on to the next one. Now remember, I multiply in the reverse order, so I incorporate the negative. So 6 times 2, that's 12, minus 0, so that's going to be 12. And then the last one, I'm just imagining all this. I don't write anything out. Negative 12 minus 2, so that's negative 14. Okay? And that's totally fine. Taking a cross product is not going to be the exciting part of any problem. It's just going to be a necessary component of it. Okay, so what do you notice about these two vectors? Is the cross product commutative? Nope, it is not. Notice that the second result is the first vector, but in the opposite direction. And that should make sense because when you take a determinant and you interchange two rows, it changes the sign, if you remember your properties of determinants. Anyways, moving on, let's prove that a vector A crossed with itself yields the 0 vector for all vectors A in 3-dimensional vector space. Okay, so you always want to start off your proof with defining what quantity you're working with. So let A be the vector. It's in three-dimensional vector space, so it has components A1, A2, A3. Okay, so since it's a proof, I'm not going to do the whole cross product in my head. The whole point is to prove that this is true. So if I just wrote A cross A equals a 0 vector, I'm not showing that I actually proved anything. Okay. So we have on the top row I hat, J hat, K hat, and then I'm going to put A1, A2, A3 in the second and third rows. Okay, now no step skipping, guys. So we have I hat times, so you can imagine we're going to have A2 times A3 minus A3 times A2 minus J hat times, I'm going to have A1, A3 minus A3, A1. And then lastly, we're going to have plus K hat times, and then the determinant of the 2 by 2 that's left over is going to be A1, A2 minus A2, A1. Okay, well notice I have I hat times 0 minus J hat times 0 plus K hat times 0. So this is the vector 0, 0, 0, which is the 0 vector. So we completed the proof. Good. Now probably the most useful aspect of cross products is given in the following theorem. The vector A cross B is orthogonal to both vectors A and B. So it's mutually orthogonal to the first two vectors that you crossed in order to find that vector. And the proof of this theorem is in many books. It's pretty straightforward, but it's tedious algebra, so we're not going to work on it right now. But say you were asked the following problem. So find two unit vectors that are orthogonal to both I plus j, I hat plus j hat, and I hat, excuse me, minus j hat plus k hat. So we need two unit vectors that are orthogonal, that are mutually orthogonal to both these vectors. So what I'm going to do is take their cross product. Okay, let's use my little shortcut. You're going to love it. So I hat plus j hat, that's 1, 1, 0. I hat minus j hat plus k hat, that's going to be 1, negative 1, 1. We're going to take their cross product, okay? And see if you can do it in your head. Okay, so if you want, you can write out an I hat and a j hat and a k hat, but you can just imagine it, all right? So you're going, crossing out that first column and row. What's the determinant of the 2 by 2 that's left over? It's just going to be 1. Okay, moving on. Now, remember, multiply in the opposite order. So you're going to do 0 times 1 minus 1 times 1. So this is negative 1. And then lastly, ooh, my little 1 went away. Okay, and then now cross out that last column in top row. Determinant of the 2 by 2 that's left over there is going to be negative 1 minus 1. So that's negative 2. Okay, so that's the result. That's the cross product of these two vectors. So I know this vector is mutually orthogonal to each of the original. However, the problem's asking for two unit vectors. So how can I make this a unit vector? Well, I need to divide by its magnitude. So what's the magnitude of this vector? It's going to be the square root of 1 squared plus negative 1 squared plus negative 2 squared. So the magnitude is rad 6. And how do I find two unit vectors? Well, one of them I'm going to keep in this same direction, and then the other one I'm going to multiply by a negative sign. So U1, unit vector number 1, is 1 over rad 6 times 1, negative 2. And then unit vector number 2 is going to be negative 1 over rad 6 times 1, negative 1. Oh, negative 2. Okay, So they're in opposite directions, but that will still maintain that they're mutually orthogonal to the first two vectors. Okay? Now, since the cross product yields a vector, we want to know what the direction of that vector is and its magnitude. Now, the direction is given by the right-hand rule. And the right-hand rule, if maybe you've taken some physics, you're familiar with it already, but just in case you're not, if the fingers of the right hand are curled from vector A toward vector B, and this is when you're taking A cross B, remember the order matters, then the thumb will point in the direction of A cross B. Okay? And in order to determine the magnitude of the cross product, we expand the expression magnitude of A cross B squared. And there's more tedious algebra, so we're just going to cut to the chase. Basically, you get down to the point where you have A cross B squared. The magnitude equals magnitude of A squared times magnitude of B squared sine squared theta. And then you can just take the square root across the whole thing, and you would have magnitude of A cross B is equal to the magnitude of A times the magnitude of B times sine theta. So this gives us the following theorem. If theta is the angle between two vectors, A and B, with theta being between 0 and pi, then the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times sine theta. Okay? So now let's recap basically what we've seen so far about the cross product. A cross B is a vector with magnitude A cross B, which is equal to magnitude of A, magnitude of B, sine theta. What else do we know about this vector? Well, it's oriented by the right-hand rule. And then lastly, and probably most importantly, it's orthogonal to both vectors A and B. Okay? Now remember, we were able to use the dot product to determine that two vectors were orthogonal. Remember, if we took the dot product of two vectors and the result was 0, then that meant cosine of the angle between them was 0, which meant that the angle was 90 degrees, so they were orthogonal. Now, since the magnitude of the cross product is equal to the magnitude of A times magnitude of B times sine theta, we can use the cross product in a similar way to show that two vectors are parallel. So if the two vectors are parallel, then that means the angle between them is either 0 or pi, right? And in that case, sine of 0 and sine of pi are both 0. So that would mean if the magnitude of A cross B is 0, then the vectors are parallel. In practice, are you really going to do this? We've already discussed how to find whether or not vectors were parallel. We discussed it in one of the first few lessons. Remember, two vectors are parallel if they're scalar multiples of each other. And that's way easier to verify than sitting through the whole process of taking a cross product. So in practice, you're probably not really going to use that. It's easier to determine whether two vectors are parallel by showing that one is a scalar multiple of the other. And that's honestly what we're going to do the majority of the time. Okay? Now let's look at some other applications of the cross product. You might be thinking it's pretty worthless, right? Okay, so the statement magnitude of A cross B equals magnitude of A times magnitude of B times sine theta can also be examined geometrically. So consider the parallelogram that's determined by vectors A and B, where vectors A and B have the same initial point. So I'm going to draw a parallelogram here. Here's vector A, and then this is going to be vector B. Okay, and they have the same initial point, and so we're going to create a little parallelogram here. And I'm going to call this angle here theta. Do you remember how to find the area of a parallelogram? You need to know its height, right? So the area of a parallelogram it's basically like how you find the area of a rectangle, because you take this little triangle and you imagine lopping it off and pasting it here, and then you have a rectangle. So that's why the area of a parallelogram is just equal to the length of the base times its height. Okay, well, the length of the base, that's not hard. I know that's going to be the magnitude of vector B. What about the height? Oh no, what can we do? Well, notice we have a little right triangle there, don't we? And sine of theta, that's going to be the height over magnitude of A. So that means the height is equal to magnitude of A times sine theta. And this expression hopefully looks familiar. We've written it out like 3-4 times by now. This is the magnitude of A cross B. Ooh. So this allows us to conclude that the magnitude of the cross product provides us with the area of the parallelogram determined by the vectors. And this we will use, especially with later in our calculus journey together. Okay, so moving on, let's look at some of the properties of the cross product. The familiar commutative and associative properties do not hold. We looked at that in the first example where we computed a cross product, right? And we saw that when we commuted or interchanged the order, the result was a vector in the opposite direction. And other properties, though, are valid. So here we've stated, okay, if you interchange the order, you get a vector with the opposite sign. You can move around a scalar using the associative and commutative properties. That's fine. And the cross product distributes over addition. Okay. But you have to be careful here when you're mixing the dot product with the cross product that the order remains intact, okay? So as a note, keep track when you're studying these properties of which ones are scalars and which ones are vectors, okay? Now the expression from property number 5 is called the triple scalar product. So I'm going to box it here. And we're going to focus right now on A dotted with B cross C. Notice the result here is going to be a scalar, not a vector, right? Because when you take B cross C, you get a vector, but then when you dot that with A, you're going to get a scalar back. And the geometric interpretation is of interest to us. So consider the parallelepiped determined by vectors A, B, and C. So previously we looked at a parallelogram, right? That was created by two vectors, A and B. Now we're going to look at a three-dimensional solid created by three vectors. And say we want to know what its volume is, okay? So how do you get the volume of a solid? Well, you take the area of its base and you multiply by its height, right? Well, let's see here. how would I figure out the area of the base of this parallelogram? Notice the base is a parallelogram formed by vectors b and c. So the area of the base is going to be the magnitude of the cross product of b and c. That's no problem. Now what about the height? Well, the height is not necessarily vector a, right? Because the height has to be orthogonal to the base. That's the height. And remember, I don't want the height to go up too high or too low. I want it exactly as tall as across the top here. So how would I do that? Well, I wish there was some way I could take vector A and project it along a vector that's orthogonal to the base. Well, I can. So remember, the height that we want is going to be the scalar projection. Oh, here come the projections again. So it's the scalar projection of vector A along, I need a vector that's perpendicular to the base. What vector is perpendicular to the base? B cross C. Okay, so if I want the scalar projection of A along B cross C, then I'm going to take the scalar component of A along B cross C. Okay, now why do I need absolute value? Well, just in case that angle ends up being greater than 90, then I want to make sure that the height is not going to be negative. Okay, and so here let's expand. So we're going to have B cross C and then A dotted with B cross C divided by the magnitude of B cross C. So that's going to cancel out here. And then I'm left with the absolute value of A dotted with B cross C. Okay, so the volume, that looks really crooked, it's going to bother me. Okay, so the volume is the absolute value of the triple scalar product. Okay, very nice. Now let's see how we can apply this to other interesting problems. So use the triple scalar product to verify that these 4 points here, P, Q, R, and S, are coplanar. So what does coplanar mean? That they all lie in the same plane. Okay, so let's think about this. So we have 4 points here, and I want to verify that they all lie in the same plane. So P, Q, R, S. And I want to make sure that one of them isn't hanging out here. How do I know that they're coplanar? And they're telling me to use the triple scalar product. So what you're going to do is say, okay, I'm going to create 3 vectors with these guys. And I'm going to find the value of the triple scalar product. And as long as they're coplanar, that should come out to be 0. If one of those 4 points is not in the same plane, then the parallelepiped will have a non-zero volume. But if all 4 of those points are in the same plane, then they will not form a solid with any volume. Okay? So let's go ahead and construct those vectors. It doesn't matter which one you use as the initial point, but just be consistent. So if you're going to have P as your initial point, you have to do PQ, PR, PS. Or you could do QP, QR, QS. It doesn't matter. Okay, let's make our vectors. So PQ is going to be, remember, 2 minus 1, so that's 1, 4, 5. And then similarly, PR is going to be 2, negative 1, 1. And then PS is going to be 5, 2, 7. Okay, and in this case, the order doesn't matter because we're going to take the absolute value at the end anyways. All right, so we want to see what is the result from taking PQ dotted with PR crossed with PS. Okay, so let's see here. PR crossed with PS. Can you do it in your head? I mean, they're already stacked up above each other, right? So you just imagine that's gone. So you're going to have -7 minus 2, so that's -9. And then you're going to have, for the next one, imagine that this is gone, right? And then multiply in the opposite direction. So you're going to have 5 minus 14, so that's -9. And then the last one from the cross product, imagine that this guy's gone, so you're going to have 4 minus -5, so 4 plus 5, that's 9. Okay, so then now I want to take the absolute value of the dot product of PQ, which is 145, with -9, -9, 9. And we're going to get, let's see here, absolute value of -9 minus 36 plus 45, which is 0, right? And as we said, if we get 0, that means the volume is 0, which implies that all 4 points are coplanar. Okay, fantastic. One last example here. So given points, these are points, not vectors, P, Q, and R, find a vector orthogonal to the plane containing P, Q, and R. Okay, so imagine it this way again. So we have a plane. And then it contains the points P, Q, and R. And I want some vector that's orthogonal to the plane. Okay, well, how would I find it? Well, what I could do is make two vectors here, PQ and PR, take their cross product, and the result is going to be a vector that's orthogonal to the plane. So let's do that. So PQ would have components 2 minus 1, so that's going to be 1, 4, 5 minus -1, that's 6. And then PR is going to be 2, 1, 8. And so PQ crossed with PR is going to be, are you guys good at doing it in your head yet? You're in Calc 3, come on, you can do it. So imagine that's crossed out, imagine I hat, J hat, K hat's crossed out, so that's going to be 32 minus 6, so that's 26. Okay, next one. Imagine this is gone, top row's gone. Now multiply in the opposite direction. So you're going to do 12 minus 8, so that's 4. And then last one, that's going to be 1 minus 8, so -7. Okay, so there's a vector that's orthogonal to the plane. It didn't say anything about it needing to be a unit vector or anything. And I would need to use the right-hand rule to figure out if it went upward or downward with respect to the plane. Good. Part B asks us to find the area of the triangle with vertices P, Q, and R. So we're going to make a triangle now out of these three. Let's move this, beautiful. And it wants the area of that triangle. Well, basically, what I could do is find the area of the parallelogram created by the two vectors PQ and PR, and then just cut it in half, and that'll give me the area of the triangle. So the area is equal to 1/2 of the magnitude of PQ crossed with PR. And cool thing is, we already have that cross product, so let's go ahead and use it. So I have 1/2 times the square root of 26 squared plus 4 squared plus -7 squared. And this comes out to being something kind of messy, so we'll just round it to 13.6. Okay, so that concludes the lesson on the cross product. These are going to be very useful for the rest of the course, so make sure that you understand it and can compute it thoroughly.